Hello. Here we'll look at an example of matrix multiplication. Appearing in seemingly unrelated mathematical domain. So let's imagine what is called a graph, a precisely directed graph, which mathematically speaking will be a set of vertices and a set of edges. So V is a set of vertices of the graph, E is the set of edges. And the thing which makes it a graph is two functions really, which says that for each edge we have the source and the target, which are vertices. So that mathematical data is called directed graph. And we can associate a natural matrix even better. We can record the graph by just a matrix, just called the adjacency matrix. Which is a square matrix with as many rows and columns as vertices. So rows and columns are labeled by vertices, and the position labeled by vertex A for the row and vertex Y for the column will be a number, a natural number, which is just recording how many edges we have starting at X, at ending at Y. So matrix entries are just counts of edges starting and ending at certain places. A quick example. Let's take 3 vertices and 3 edges and arrange them like that. To make a 3D matrix, we have to label our vertices, call one first, some other second, and the remaining third. And then the matrix, according to this rule, if we fix X, if we look at the vertex, then entries of the corresponding row will be numbers of edges going to the all other vertices, including the vertex itself. So from 1 we only have one edge going to the second one. So neither to the first, none to the first, 1 to the second, and none to the last. Looking at vertex number 2, we have again only one edge emanating from it and going to the vertex number 3. So there's nothing going to number 1, nothing going to number 2 itself, just 1 to number 3. And the last third row is what counts what comes out the third vertex, and there's only 1 going to number 1. So nothing to number 2, no edges in this direction, no self edges, no loops there. So that is the matrix of this graph. That is the adjacency matrix of this graph. What is and it is just a complete record of the graph, having a matrix with coefficients. So will be as many as elements in the vertex set, and coefficients are non-negative integers. Any such matrix gives us a graph. It's just the same data. What is this data convenient for is, for example, counting path in this graph. What we can do, we can just take this matrix, and since it is a square one, we can multiply it with itself as many times as we like. And then look at the entries of this nth power. Then the entry sitting in row labeled by X and in column labeled by Y will be just counting of length n from X to Y. So for example, there is only one path from 1 to 2, and that corresponds to the entry in the first power. And if we look at number of paths from 1 to 3, we'll just have 1 again, but there will be no path of length 2 from 1 to itself. And that would correspond to, according to this statement, will correspond to the entries in the square. So let's see, first let's just look at the quick argument of why this is true. The best way of, maybe not the best, but yeah, the shortest way of proving it is by induction, is by looking at the previous length of path, say n minus 1, and assuming that we have this statement already, and then arguing that we should have the next one. And it is easy because elements in the nth power itself can be computed inductively as a product of the previous power and the matrix again. So matrix entries in the nth power will be given by the sum of products of matrix entries from here and from A. And I will write it in a compact notation. The sigma will represent a lone sum, and summands will be labeled by some what is called running index. I'll call it that. And it is an arbitrary vertex. That will be the entry of that matrix multiplied by the corresponding entry of the second matrix of just A, and then summed up will give me the matrix entry in the product of the two. So that will be computing entries in the nth power. And then by induction, these numbers count path starting at X and ending at some vertex Z of length n minus 1. And then we have multiplying the number of such paths by the number of connections between Z and Y. And that is indeed counting all paths uniquely, because what we can do with every path is to look at where it, which vertex it takes before reaching Y, and that will be determining the Z, and then the path from X to Z will be counted by this number, and then the number of last moves in the path will be accounted by this entry. So that is a quick proof of the statement. Let's put it into use computing powers of this matrix A in the example. Computing the square, we have to multiply the matrix with itself. And in this example, we can do it using the graph, seeing where we have path of length 2, or we could do it using matrix multiplication. So we have to compute 9 entries using matrix multiplication, and say this entry is the result of matching the first row and the first column, and they match in the 0 way, so that the sum of products of their coordinates is 0. This entry comes from matching this row and that column, and again, non-zero entries misalign, giving us 0. That entry when we match this row and this column, so this time 1 in the row meets 1 in the column, giving us total 1 in the product. Continuing, we have to multiply entries of this row by entries of this column and sum them up, and that again gives us 1. After that, we'll have to see mismatch giving us 0 when we take this row and that column. And again, the mismatch happens in here, giving us 0. So here we have 1, 0, 0 by 0, 0, 1. That is 0. And that is 1 again. And finally, this is 0. So we will see a matrix which is similar to the original one, but symmetric with respect to the flip Illinois diagonal. And if we continue computing the powers and computing the third power, we will have to multiply the matrix with its square, which is this answer. And this time something even nicer happens, because when we compute this entry, we will see 0, 1, 0 matching with 0, 1, 0, giving us 1. Then we will have 0, 1, 0 with 0, 0, 1, mismatch giving us 0, 0, 1, 0, and 1, 0, 0 gives us 0 again. So here we'll have 0, 0, 1, 0, 1, 0, 0, 0, 0, 1, and 0, 0, 1 gives us 1 again on the diagonal. And here we'll have 0, so splitting it up, we'll have 2 zeros here and 1 again in the last diagonal place because of 1, 0, 0 matching with 1, 0, 0 again. So that is nothing but the identity matrix. And that means that in this example, the powers of our matrix A are periodic. Because when we compute the fourth power, we will be multiplying A with the identity, and the result will be A. So writing the answer for powers of A is now easy if we are computing the power which is a multiple of 3, we will have the identity, because we will be just multiplying cubes some number of times. If the power we are computing is 1 plus a multiple of 3, we will have matrix A, original one. And if it is 2 plus a multiple of 3, if the remainder is 2, then we will have what is A squared, this matrix. So that takes care of all possible paths of all possible length in the graph. So interpreting this result using the combinatorics of the graph, what it says is that we only have path of length 2 between 1 and 3, 3 and 2, and 2 and 1. That is this code. And all the rest is the same. And here, this result is saying that path of length 3 will only be self path. So we'll be starting and ending at the same place because of the graph structure. If we do 3 steps in the graph, we are coming back to where we start. So that is the code for the identity matrix. Let's do a couple of more examples. Again, looking at 3 vertex cases. So let's now look at what is called a complete graph. Any 2 vertices are connected, giving us all these connections. When we write the matrix of this graph, it will be all one matrix. Any 2 vertices connected by a unique edge. So this matrix, when we compute its square, it doesn't matter where we compute, which entry we compute, because all the rows and all the columns are the same. So doing this computation once will give us the answer everywhere. And say for this entry, we are multiplying 1, 1, 1 with 1, 1, 1 again. And the sum of products is 3. And so we will have the matrix which is just filled with number 3. And that is nothing but 3 times the original matrix A. So we have the recursion for computing the powers. Any power can be now iteratively computed by taking the previous power and multiplying it with A again, and the previous power is some multiple of A, so we have this answer for powers, which can be turned into a statement about the number of paths in the complete graph. The number of paths of length n is 3 to the power n minus 1. So number of paths of length 1 from any vertex to any other vertex is 3. That is this matrix, right? From 1 to 1 is 1 loop. From 1 to 2 is 1h. From 1 to 3 is again 1h. The number of paths of length 2 is number of paths of length 1 is 1 for each pair of vertices. Number of paths of length 2 is 3. So if we want to count how many ways in 2 steps we can go from here to there, this is 1, this is this, and this is the other, is another, and then starting with a loop and then doing again the connection is the third one. So that is a generic answer for arbitrary length. And one more example when we get rid of self loops in the graph, and look at this. So that will correspond to the matrix where we don't have diagonal entries, where on the diagonal we will have zeros, but everywhere else we will still have ones. And of course I can compute the square of this matrix directly, but instead I will do some algebra of matrices which will simplify this computation. With respect to the previous one, so maybe I should call it differently to distinguish from this A. And in terms of the previous A, it is A without the identity matrix, because the identity matrix will be just all ones on the diagonal and zeros everywhere else. So if I subtract this matrix from that, I will just get what I have here. And so computing the powers, like the square, now I can use simple arithmetic. So I'm computing the square of the difference of two matrices and writing it according to binomial formula. Expanding it will give me this. The square of A minus twice A plus identity. The square of A is known to me now, is 3A, so I can put it in here and see what happens. It will be just A plus identity. But in terms of my adjacency matrix B for this graph, it will be A minus I plus twice identity, and that is what is called B now. So B squared is B plus twice identity matrix. And that can be iterated now computing any power. But here, before we do that, we can see what this answer tells us. So what it tells is that the number of paths of length 2 between different vertices will be just 1. And self path of length 2 will be 2, will be double. And it is easy to see because if we start at this vertex and we look at the path of length 2 with which ends at this vertex, we have this and we have this. But if we go to that, we have only, if we go to that, from 1 to 2, we have only one path which is going this way and then going this way. So computing path of length 3, we have to compute the cube, and now we're just using this as a recursion, expanding B squared as B plus twice identity and multiplying it with B, using distributivity, writing it as B squared plus twice B, and then again expanding B squared as B plus twice identity, and then we have 2B on top, and that is 3B plus twice identity. So path of length 3 will be between different vertices will be counted by 3, but self path will still be doubled. So the path of length 3 starting at this vertex and ending at this vertex will only be possible by doing this, and that, and this, and that. But if we look at 2 different vertices, we have 3 connections. We'll leave it to you to see what they are. Just continuing with computations, path of length 4 will be visible as entries of this product, and cube is 3b plus 2i, multiplying it by the adjacency matrix again, writing it as 3b squared plus 2b, expanding b squared again as b plus 2i, and adding to b, we will have 5b plus 6i. So self path of length 4, there are 6 for each vertex, and for different 2 there will be 5. One warning, we used this binomial formula, but in general, if the matrices which we take the square of the sum of, if they don't commute, then the binomial formula will not be true. Instead, since AB, and the BA here, if AB and BA are different, and if we distribute the sum from the sum again, we will have a slightly different expression. We'll have squares of A and B, and then we'll have the sum of AB and BA. But here it's all good because one of the matrices B is it's not that B, but here one of the matrices under the inside the sum is the identity or minus identity, and for that matrix, multiplying it with A from the left or from the right gives us the same answer. So if the 2 matrices commute, we still have the standard binomial formula working for us. That is it for this example. See you later.